41 light years. From where you're sitting right now, there's a planet so hot that its surface stays permanently molten, glowing like an open wound stretched across an entire world. Scientists have known about this planet for over 2 decades. But this month, the James Webb Space Telescope looked at it one more time, and what it found didn't match a single one of the leading predictions. Not one. Every major model built to explain this planet over the last 20 years just quietly stopped making sense. So what actually is 55 Cancri E? Why did it take the most powerful telescope ever built to finally understand it? And what does this tell us about how rocky planets survive, or don't survive, next to a star? Real quick, before we dive in, I want to know something. If you could safely observe any planet in the galaxy up close, just for a moment, which one would you pick? Drop it in the comments. I genuinely read these. And if you're new here, this channel breaks down real space and Earth science stories like this one every single week. So hit subscribe if that's your kind of thing. All right, let's get into what Webb actually found. 55 Cancri E was first discovered back in 2004, orbiting a star that's just barely visible to the naked eye on a clear night, roughly 41 light years away in the constellation Cancer. From the very beginning, this planet stood out as strange. It's a super-Earth, meaning it's bigger than our planet, but still rocky rather than gaseous, measuring about 1.88 times Earth's radius and roughly 8 times Earth's mass. But here's the detail that made scientists' jaws drop when they first calculated it. This planet completes an entire orbit around its star in just 17 hours. Not 17 months, 17 hours. For comparison, Mercury, the closest planet to our own sun, takes 88 days to complete a single orbit. 55. Cancri E is so close to its star that it doesn't experience a year in any sense we'd recognize. It experiences one every single day, over and over, forever. Being that close to a star does something extreme to a planet. The dayside of 55 Cancri E is tidally locked, meaning the same side always faces the star, permanently, the same way the same side of our moon always faces Earth. That dayside is subjected to such intense radiation and heat that early researchers assumed the surface had to be an ocean of molten rock, a literal sea of lava stretching across the entire hemisphere facing the star. For years, the leading theory was that this planet had, at best, a thin, wispy veil of vaporized rock clinging to its surface, not a real atmosphere in any meaningful sense, just rock boiled directly into gas by the heat. Some early estimates of the planet's density even led a few astronomers to wonder if it could be a so-called diamond planet, a world with a carbon-rich interior compressed into something resembling an enormous gemstone. That theory made headlines for years. It also turned out to be almost certainly wrong. Here's where Webb changed everything. Researchers pointed the telescope's instruments at 55 Cancri E and started measuring something specific: its thermal emission, essentially the heat energy the planet gives off as infrared light. If the leading theory was correct, if this planet really was just bare molten rock with no real atmosphere trapping and redistributing heat, then the dayside temperature should have measured somewhere around 4,000 degrees Fahrenheit, roughly 2,200 degrees Celsius. Instead, Webb's MIRI instrument measured a dayside temperature of about 2,800 degrees Fahrenheit, right around 1,540 degrees Celsius. That's still hot enough to melt nearly every rock and metal we know of, but it's over 1,000 degrees cooler than the bare rock model predicted. And in planetary science, a gap that large isn't a rounding error. It's a signal that something is actively moving heat around the planet that shouldn't be there if the surface were truly airless. The research team, led by scientist Renyu Hu, explained that lava flows alone simply couldn't account for that kind of heat redistribution. Molten rock can carry some warmth from the dayside toward the night side, sure, but not efficiently enough, not fast enough, to explain a 1,000-degree temperature drop like this. The far more likely explanation, according to the data, is a genuine volatile-rich atmosphere, an actual layer of gas wrapped around this planet, actively transporting heat from the blistering dayside toward the permanently dark night side, the way an atmosphere is supposed to behave. When the team then analyzed data from Webb's NIRCam instrument, they found patterns that lined up with exactly that conclusion. A real dynamic atmosphere, not just a thin veil of vaporized stone. Then came an even more detailed follow-up study, using Webb to observe 5 separate eclipses of 55 Cancri E passing behind its star, comparing each set of readings against long-standing models of how rocky exoplanets are supposed to behave. What they found didn't match the old prediction of a static carbon monoxide and carbon dioxide atmosphere sitting quietly on the surface. Instead, the data pointed to something far more dynamic, an atmosphere made mostly of carbon monoxide, with smaller amounts of carbon dioxide, and surprisingly, an abundance of hydrogen. And the differences observed across those 5 separate eclipses weren't random noise. They suggested the atmosphere itself is actively changing, shaped by gases actually escaping from the planet's molten interior in real time. In other words, this isn't a fixed, stable atmosphere sitting still. It's an atmosphere connected directly to what's happening inside the planet, constantly being replenished by outgassing from below. Some of the researchers even proposed that this outgassing might be creating temporary clouds that could briefly cool sections of the surface before dissipating as fresh gas is released from underneath. Scientists describe this connection using something called the planet's redox state, essentially the chemical balance between oxygen and hydrogen or iron deep inside a planet's interior. On 55 Cancri, hydrogen appears to be strongly favored over oxygen in that internal balance. And that imbalance is exactly what's producing the hydrogen-rich atmosphere Webb detected. The researchers wrote that since the secondary atmospheres of rocky planets are set by the composition of the interior and the outgassing that follows, the atmosphere itself becomes a direct, readable signature of what's happening deep inside a planet we'll never physically visit. Think about that for a second. By studying gas floating in a paper-thin layer around a planet 41 light-years away, scientists can start to read the chemistry of that planet's molten core. Why does any of this matter beyond just one strange, distant world? Because 55. Cancri isn't alone. Lava planets like this one, worlds so close to their stars that their surfaces stay permanently molten, have become one of the most active areas of exoplanet research over the last decade. Planets like K2-141b, L9859d, TOI 561b, HD 63433d, and CoRo T7b all share the same brutal category. Tidally locked, blisteringly hot, orbiting their stars in anywhere from roughly 6 hours to a little over a week. Every single one of these worlds gives scientists a completely different natural laboratory for understanding something we genuinely cannot recreate here on Earth: how a rocky planet's atmosphere behaves when it's being actively cooked and outgassed by extreme heat in real time. Earth's own atmosphere formed and evolved over billions of years through processes we can only partially reconstruct from geological evidence. On 55 Cancri, scientists may be watching an early-stage version of that same fundamental process, atmosphere formation, through volcanic outgassing, unfolding right now, observable, in a system we can actually point a telescope at. This discovery also says something important about how science actually moves forward. For years, the leading model for this planet was a bare, rocky world with barely a wisp of atmosphere, or possibly a diamond interior. That theory wasn't lazy or careless. It was the best conclusion available given the instruments and data scientists had at the time. Webb didn't just add a new detail to that picture, it fundamentally overturned it. And this is genuinely how good science is supposed to work. A better instrument arrives, better data comes in, and researchers are willing to abandon a theory they've defended for 2 decades the moment the evidence stops supporting it. That's a very different story than the version we often see clickbaited into a headline. Nobody panicked, nobody hid the data. A research team quietly did the work, submitted their findings to Nature Astronomy for peer review, and let the results speak for themselves. It's genuinely useful to compare 55 Cancri to something a little closer to home, Jupiter's moon Io, the most volcanically active body anywhere in our own solar system. Io's volcanism is driven by something called tidal heating, the constant gravitational squeezing and flexing caused by Jupiter's immense gravity as Io orbits, which generates enormous internal friction and heat, enough to power hundreds of active volcanoes across a moon smaller than our own. 55. Cancri-E's volcanism works through a completely different mechanism. This isn't a world being squeezed by a nearby gas giant, it's a world being scorched directly by its own star, orbiting so close that stellar heat alone is enough to keep its entire dayside in a permanently molten state. Comparing these two worlds side by side gives researchers a rare opportunity. 2 extremely volcanic bodies driven by 2 entirely different physical processes. Tidal flexing in one case, direct stellar heating in the other, both offering a kind of natural experiment for understanding how volcanic activity shapes a world's atmosphere and surface over time. It's also worth understanding a little about the specific tools Webb used to pull off this observation, because they highlight just how far exoplanet science has come. The MIRI instrument, short for mid-infrared instrument, is built to detect longer wavelength infrared light, the kind best suited for measuring an object's temperature from its heat signature alone, which is exactly how the team first noticed the dayside was cooler than expected. NIRCam, the near-infrared camera, operates at shorter infrared wavelengths and is better suited for picking up the subtle spectral fingerprints left behind by specific gases, like the carbon monoxide and hydrogen signatures identified in this study. Using both instruments together, one to measure raw temperature, the other to identify the exact chemical makeup of what's producing that temperature pattern, is what allowed the research team to move from a general observation, this planet is cooler than it should be, to a specific, testable conclusion, this planet has an active, outgassed atmosphere with a particular chemical signature tied directly to its interior. Because none of these worlds are visible through a telescope the way you'd photograph a planet in our own solar system, at 41 light-years away, 55 Cancri A is far too small, faint, and close to its blindingly bright host star for any camera to simply capture a picture of it directly. Instead, astronomers originally detected it using a technique called the radial velocity method, which doesn't look at the planet at all, it looks at the star. As the planet orbits a star, its gravity tugs the star back and forth ever so slightly, causing the star's light to shift almost imperceptibly toward red and then blue as it wobbles toward and away from us. By measuring that tiny, rhythmic wobble with extremely sensitive spectrographs, astronomers can calculate a planet's mass and orbital period without ever seeing the planet itself. Later, astronomers got lucky with 55 Cancri A in a way that doesn't happen for every exoplanet. They observed it transiting, meaning it passes directly between its star and our line of sight from Earth, causing a tiny, measurable dip in the star's brightness roughly every 17 hours. That transit is what eventually allowed scientists to calculate the planet's actual physical size, and it's also exactly what makes a planet like this one so valuable for a telescope like Webb. Because during a transit or an eclipse, when the planet passes behind its star, astronomers can isolate the planet's own light signature from the overwhelming glare of the star itself. And that's precisely the technique the research team used across those 5 separate eclipse observations. None of this was easy data to collect, even for an instrument as powerful as Webb. The star 55, Cancri itself, is what astronomers call bright, sitting right at the edge of naked eye visibility under clear, dark skies, which sounds like it should make things easier, but it actually creates the opposite problem. A star that bright can overwhelm even Webb's extraordinarily sensitive instruments, effectively drowning out the comparatively tiny signal coming from the planet itself. Dr. Hu, the lead researcher on this project, has openly acknowledged that this particular dataset turned out to be more challenging to interpret than almost any other observation Webb has produced. That's a genuinely remarkable admission, considering everything else Webb has successfully observed since it launched: distant galaxies billions of light-years away, the atmospheres of far fainter exoplanets, detailed structures within star-forming nebulae. And yet a relatively nearby, well-known lava planet orbiting a naked-eye star turned out to be one of the messiest, noisiest datasets the team had worked with, which says a great deal about just how difficult it is to tease a planet's whisper of a signal out from underneath its star's roar. There's also a broader question worth asking here. Why does any of this matter beyond satisfying curiosity about one unusual planet? Lava worlds like 55 Cancri A sit at a genuinely important edge of planetary science, the boundary between planets that can hold on to a stable, breathable style atmosphere and planets that lose everything to their stars' relentless heat and radiation. Understanding exactly how atmospheres form, survive, or get stripped away on a planet subjected to extreme heat gives scientists a crucial reference point for a much bigger question that gets asked constantly in astronomy. What actually determines whether a rocky planet ends up habitable, or ends up like this? A permanent ocean of fire wrapped in a shifting, volcanically fed atmosphere. Every lava planet we study in detail adds another data point to that much larger puzzle. One planet at a time, one impossible extreme at a time. This also isn't the end of the story for 55 Cancri A. It's really just the beginning of a much deeper investigation. The research team has already indicated this is the kind of data set that warrants repeated observation over time, precisely because the atmosphere appears to be dynamic rather than fixed, changing between one eclipse and the next as outgassing ebbs and flows from the planet's molten interior. That means future observations with Webb could eventually let scientists build something like a weather record for this planet, tracking how its atmosphere shifts, thickens, or thins over months and years, the same way meteorologists track storm systems here on Earth, just applied to a world where the entire concept of weather is being generated by volcanic gases erupting from an ocean of lava rather than water evaporating from an ocean of liquid. There's also renewed interest in comparing 55 Cancri E directly against the small but growing list of other known lava worlds, to see whether this same pattern, a hydrogen-rich atmosphere fed by active outgassing, shows up elsewhere, or whether 55 Cancri E turns out to be its own unique case, even within this already extreme category of planets. Given how much this single planet has already overturned 2 decades of assumptions, most researchers in this field seem to expect more surprises rather than fewer as observation time increases. So here's where that leaves us. 41 light-years away, there's a planet completing an entire orbit every 17 hours. Its dayside, a permanent ocean of molten rock, wrapped in an atmosphere that shouldn't exist according to the old models, an atmosphere actively fed by gases escaping from its molten interior, possibly even generating clouds that form and vanish within hours. It is, by any reasonable definition, one of the strangest, most hostile worlds we've ever managed to study in this kind of detail. And we only understand any of this because a 2-decade-old theory was willing to be proven wrong. If a story like this is the kind of thing that makes you want to look up at the night sky a little differently, that's exactly why this channel exists. We'll be back soon with the next discovery, the next mystery, the next place in the universe worth understanding a little better than we did yesterday. Until then, take care of yourselves, stay endlessly curious, and I'll catch you in the next one.